Hello and welcome, future physicists and engineers. If you're tackling grade 12 physical science, you know that mechanics is a huge part of the syllabus and a major chunk of your final exam. But don't worry, by the end of this video, you'll have a rock-solid game plan. We're going to break down the entire mechanics syllabus from Newton's laws to work, energy, and power. And most importantly, I'll show you the common pitfalls to avoid so you can ace those exams. Ready? Let's dive in. Mechanics is all about motion and the forces that cause it. Everything starts with the legend himself, Sir Isaac Newton. His three laws are the foundation. Newton's first law, the law of inertia, is simple. An object stays at rest or in constant motion unless a net force acts on it. Think about it. When a car suddenly stops, your body lurches forward. That's inertia. Your body wants to keep moving. This is why seatbelts are non-negotiable. Now, for the big one, Newton's second law. This is your go-to formula for almost every mechanics problem. Net force equals mass times acceleration, or F net moins masse par ma. It tells us that an object accelerates in the direction of the net force. The bigger the force, the bigger the acceleration. The heavier the object, the smaller the acceleration. We'll use this for everything from a single block sliding on a table to complex pulley systems. Then there's Newton's third law. For every action, there's an equal and opposite reaction. If you push on a wall, the wall pushes back on you with the exact same force. The crucial thing to remember here is that these action-reaction forces always act on different objects. So they never cancel each other out when you're calculating the net force on a single object. This is a common point of confusion, so lock that in your mind. Before we can use F net times ma, we need to be masters at identifying all the forces acting on an object, and the only way to do that is with a free body diagram. This is non-negotiable. It's the first step for every single dynamics problem. First up, we have the gravitational force, Fg, or weight. It always acts straight down towards the center of the Earth. You calculate it as mass times g, the acceleration due to gravity. Next, the normal force, Fun. This is the support force from a surface acting perpendicular to that surface. It's the reason your textbook doesn't fall through your desk. A huge warning here. The normal force is not always equal to the weight. It's only equal to the weight on a flat, horizontal surface with no other vertical forces. This mistake costs students countless marks. What happens on an incline? This is where things get interesting. The weight, Fg, still acts straight down. But we need to resolve it into components. We split it into a component perpendicular to the slope, which is balanced by the normal force, and a component parallel to the slope, which is what tries to pull the object down the incline. Remember, the parallel component uses the sine of the angle, and the perpendicular component uses the cosine. Practice this until it becomes second nature. Then we have friction, Ff, the force that always opposes motion or the tendency of motion. It's caused by microscopic bumps on surfaces locking together. We have static friction, which you must overcome to get something moving, and kinetic friction, which acts once it's already in motion. That's why it's harder to push a heavy box from rest than to keep it sliding. Both are calculated using a coefficient of friction multiplied by the normal force. Notice how the normal force is key here? Get it wrong, and your friction calculation will be wrong too. And finally, tension, Fft. This is the pulling force in a rope or a string. It always pulls away from the object, along the direction of the rope. In problems with connected objects, tension is the force that links their motion together. Now let's talk about something that trips up so many students, positive and negative signs. In physics, these signs just mean direction. Before you solve any problem, you must choose a positive direction and state it clearly. For example, let's take right as positive. Any force or motion to the right is then positive, and anything to the left is negative. When you add up your forces to find the net force, you must use these signs. Friction, since it opposes motion, will almost always be negative if you've chosen the direction of motion as positive. Be consistent. Your final answer for acceleration will have a sign that tells you its direction relative to your chosen positive direction. Okay, let's move on from forces to momentum. Linear momentum is simply an object's mass times its velocity. It's a measure of how much oomph a moving object has. This leads us to the impulse momentum theorem, which says that a net force applied over a time interval, that's impulse, causes a change in momentum. This is why airbags work. They increase the time of impact, which decreases the force on you. And that brings us to one of the most powerful principles in physics, the conservation of linear momentum. In an isolated system, meaning no external forces are interfering, the total momentum before a collision is exactly equal to the total momentum after the collision. Momentum is transferred between objects, but the total amount stays the same. This is the key to solving all collision problems. Our final section is work, energy, and power. Work is done when a force causes an object to move a certain distance. The formula is work equals force times displacement times the cosine of the angle between them. Be careful, if a force is perpendicular to the motion, it does zero work. Energy is the ability to do work. We have kinetic energy, the energy of motion, and potential energy, which is stored energy due to an object's position, like gravitational potential energy. The work-energy theorem is another super useful tool. It states that the net work done on an object equals its change in kinetic energy. But what if we have forces like friction? Friction is a non-conservative force. It takes energy out of the system, usually as heat. When friction is present, mechanical energy, which is the sum of kinetic and potential energy, is not conserved. In that case, we use the principle that the work done by non-conservative forces equals the change in the total mechanical energy of the system. If there's no friction, then total mechanical energy is conserved, which makes problems much simpler. Finally, power is just the rate at which work is done or energy is transferred. So let's recap the biggest exam mistakes and how to avoid them. Mistake number 1, incorrect free body diagrams, especially on inclines. Solution: always draw the diagram first, label every force, and on an incline, always resolve the weight into its parallel and perpendicular components. Don't just assume the normal force equals the weight. Mistake number 2, inconsistent signs. Solution: at the start of every problem, explicitly state your chosen positive direction and stick to it. Every vector quantity, force, velocity, acceleration, must follow this convention. Mistake number 3, confusing Newton's second and third laws. Solution: remember, F net Nenmer's MOI is for a single object. Newton's third law, action-reaction pairs act on different objects and don't go into the F net equation. And mistake number 4, mixing up energy and momentum principles. Solution: for collisions, think conservation of momentum. For problems involving changes in height and speed with forces acting over a distance, think work and energy. Always check for non-conservative forces like friction to decide which energy principle to apply. There you have it, a complete roadmap to conquering grade 12 mechanics. It seems like a lot, but the key is a systematic approach. Draw the free body diagram, choose a positive direction, apply F net for SGMA, and be mindful of your energy and momentum principles. Practice these steps over and over, and they will become second nature. You've got this. Thank you so much for watching. If you found this guide helpful, please give it a thumbs up. And don't forget to subscribe for more physics content to help you ace your exams. Keep practicing, stay curious, and I'll see you in the next video.